You came here because you want to master alkanes with a University of Cambridge graduate. Let's begin. As usual with organic topics, it's very important to understand the reactions of the organic reagent as well as the different mechanisms that are involved within the reactions itself. Usually schools will take about 2 to 3 weeks to run through this topic. Well, this is actually a very simple topic that I aim to summarize in a very short span of time for you so that you can look at this video and refer to it at any time when you're doing your revision. So alkanes are saturated hydrocarbons, and what that means as we run through in the introduction to organic chemistry is they only have single bonds. And because of that, the carbons are all sp3 hybridized. The general formula of alkanes is CnH2n plus 2. And how this is useful is when you look at a typical molecular formula of an organic reagent, for example C6H14, and you realize that this conforms to the pattern of CnH2n plus 2, you should instantly tell that this molecule is an alkane. And this is particularly useful because whenever you don't really have an idea on what an organic reagent could be from the molecular formula, you have to rely on your instincts and knowledge on these kind of general formulas. This alkane one is very, very typical, and it's often tested because this general formula is only applicable to alkanes. Alkanes are also generally unreactive, and you have to know the reasons for this. Because 1, the CC and CH bonds are strong covalent bonds, and 2, because it's saturated, there's actually no regions of high or low electron density. So just a recap, remember in my introduction to organic chemistry video that reactions are always propelled in organic chemistry from the transfer of electrons from a electron-rich site to electron-poor site. And because alkanes have neither of these, it's actually very difficult to have reactions with alkanes itself. Moving on to reactions of alkanes, the first one is combustion. I put this here even though it's not very unique to alkanes, but just a reminder that all organic reagents can undergo combustion. And you can refer to the mole concept topic for all the calculations and the equations involved in your combustion reactions for any molecule. But the most important reaction for alkanes is free radical substitution, aka FRS. Because alkanes are so unreactive, you would need a high energy source, aka UV light, in order to propel the reaction forward. The reagents and conditions are UV light, and the halogen itself, typically Cl2 or Br2. So overall, if you have an alkane and you react it with Cl2 or Br2 under UV light, you're able to do a substitution reaction. Remember, substitution reactions are replacing a certain atom with another atom, and in this case we're replacing a H with the Cl atom. It's important to understand how free radical substitution works because you'll be asked to draw the mechanism during the exam. If we look at the first step, this is initiation, and what initiation means is it starts off the whole reaction. So under UV light, the halogen will have the bond broken apart in a heterolytic fission, and what's going to happen is the 2 electrons are going to split to produce your radicals. In this case, it will be chlorine radicals. And the radicals are denoted by this dot over here, which shows that the atom or the radical itself has an odd number of electrons. Your chlorine radical is going to react with the alkane next to undergo a propagation reaction. And what this is going to do is it's going to produce an alkane radical, as you can see over here. And the alkane radical will also react with other halogens itself, which is other chlorine molecules here, and form back the chlorine radical. And this is why this is called the propagation reaction. Whenever a radical reacts with another non-radical, you'll always produce a radical from the reaction. And this is why radicals are highly reactive and very dangerous to play around with, because under the wrong circumstances, they can undergo a chain propagation reaction and cause a whole bunch of reactions that are unexpected. Lastly, we have termination. So what termination means is when a radical meets another radical, because both of them have an odd number of electrons. In math, you know that odd plus odd will always give you an even number. In this case, that is the same thing. A radical that reacts with another radical will always give a non-radical. So you can just take your combinations of radicals produced from the propagation reaction and react them with one another. So if two chlorine radicals react with one another, you can form back the halogen. A chlorine radical that reacts with an alkane radical can also give the product that you want. Or you can get another side product, which is a minor product, where the alkane radicals react with one another and form itself. Do take note that multi-substituted products are possible, and that's because radicals are just relentless. Again, I must emphasize that radicals react with anything possible. So for example, let's say you have your product over here. It can undergo another free radical substitution and form a multi-substituted product like this. And because of that, it's important to use limited halogen in your reagents and conditions in order to maximize the amount of mono-substituted products as possible. Now, we also need to understand how we can predict the ratio of mono-substituted products from my FRS. Because as I mentioned, radicals are relentless and would react with anything possible. So you can expect there are multiple mono-substituted products that are possible. But there is actually a way to predict this ratio. It mainly ties down to two factors. One is the number and type of H atom to be substituted to give the product. So there are multiple H atoms that are similar, because when you substitute those hydrogen atoms, you can get the same product as well. And also the stability of the radical formed from the substitution, which is a key point to take note. And this is because looking at the potential radical that is formed, some radicals are more stable than others. If a radical is more stable, and it will be more preferentially formed from your reaction, and because of that, the pathway or the reaction pathway is going to favor that path and form that radical instead. Now, how are radicals more stable or less stable? This is based on the electron donating R groups that are bonded to the radical carbon. So in general, R groups are very electron donating. If they can donate the electrons to the radical, the carbon radical wouldn't be as electron hungry, and therefore it would be slightly more stable than one carbon radical with less R groups itself. And the opposite effect will happen if you have electron withdrawing groups. So for example, if I have a Cl over here, the Cl is electronegative and is going to take away electrons from the carbon. And because of that, the carbon is actually more electron hungry and it is less stable to be formed. If you take a look over here, you can see how the different factors play a role in predicting the ratio of the mono-substituted product. So if you look at this typical propane, there are two kinds of hydrogens that can be substituted to give two different products. One is HA and one is HB. If you substitute HA, you'll get this product over here, which is 1-chloropropane. And if you substitute HB, you'll get 2-chloropropane. Now, if you just look at the number of H atoms, you can predict the ratio of the mono-substituted products first. And you will see that the ratio is 6:2, or to be simplified, 3:1. Because there are 6 HA atoms that can be substituted to give 1-chloropropane, and 2 HB atoms that can be substituted to give 2-chloropropane. But because of that, you would think that the statistical ratio would be 75%:25%, but that's not actually the case, because the actual ratio is actually 45%:55%, and the 2-chloropropane is actually the slightly favored product. And this is because of the stability. As I mentioned just now, stability plays a huge important role. Now, we see that the radical formed from the reaction to form 1-chloropropane is this radical over here, whereas the other one to form 2-chloropropane is this radical over here. If you take a look at both these radicals, the 2-chloropropane radical is actually a second degree radical, and therefore it has two R groups, whereas the first degree radical only has one R group. Because of that, the second degree radical with more R groups has more electron donation to the carbon radical. And because of that, your 2-chloropropane radical is more stable than the 1-chloropropane radical. And therefore, it's more favorable to be formed, and that's why the reaction pathway to form your 2-chloropropane is more favored than the 1-chloropropane. Lastly, you need to know of some environmental consequences of using alkanes as fuel. When you use alkanes as fuel in combustion, for example, you would get incomplete combustion as part of the process as well. Because of that, you can produce carbon monoxide. And the poisonous thing about carbon monoxide is that it binds irreversibly to hemoglobin and it will hinder the transport of oxygen. So because of these, you can also get respiratory illnesses and even death as well. Unburned hydrocarbons also comes from incomplete combustion, and these can form photochemical smog which gives respiratory sickness. There's also oxides of nitrogen that are formed, and this is mainly because of the high temperatures in your engines. The high temperatures are able to break the N triple bond N. Because it's a triple bond, it requires a high amount of energy to break this bond. But once it's broken, these nitrogens can form your nitric oxides. And these nitric oxides are very acidic because they can form acid rain when they react with water in the air. And these corrode your buildings and damages your agriculture and destroys your marine life because they go into your rivers. And also, oxides of nitrogen aid in forming your photochemical smog, which is bad for your respiratory system. One last thing is, of course, in combustion, you are going to get carbon dioxide from your alkanes. And because of this, we know that carbon dioxide is a greenhouse gas. The problem with that is greenhouse gases contribute to global warming. Enhanced global warming is what's going to cause the melting of your polar ice caps because of the increase in temperature of your surroundings, and the sea levels will be rising and there'll be flooding and a whole lot of other destruction of natural habitats, for example. So what can we do to curb the harmful effects of using alkanes as fuel? Well, we can use a catalytic converter, which is usually present in your engines. What this catalytic converter does is it can react with your unburned hydrocarbons and inside there is the platinum and palladium catalyst. So it will continue burning or further combusting these unburned hydrocarbons in order to get CO2 and H2O, which are much less harmful products than your unburned hydrocarbons. Your carbon monoxide can also be further oxidized with your platinum and palladium catalyst to give carbon dioxide. And your carbon monoxide can also react with oxides of nitrogen to give CO2 and N2. And this is done by your rhodium catalyst. So your catalytic converter is very important because it can help to convert these harmful pollutants into less harmful ones like CO2. So that's all for alkanes. I would advise that you take some time to go and memorize the reaction mechanism for free radical substitution, as well as practice some questions on understanding how to predict the ratio of your monosubstituted products of free radical substitution. Free radical substitution is the key takeaway from the alkane topics, and it's important that you understand this fully in order to maximize your marks for alkanes during the exams. If you like this content, be sure to hit the subscribe button below so that you can get more frequent updates from this channel. If you want to enroll in my online class, be sure to click the link below as well so that you can book a free call with me and I can go through your past year papers and go through any doubts and clarifications that you require and show you why my course is the best fit for you. I'll see you in the next lesson.